work. Thanks.
Thank you. Thank you so much, Luigi. And thank you all for the kind invitation also. Today, I'll be talking about learning to predict and respond for human-robot interaction. And the main argument I'll be making throughout the talk is that we need to tightly couple prediction and response in order to create really powerful frameworks for human-robot interaction. But before we go into any of that, I'd like to show you a small clip, an interesting clip, and I'd like you to predict or anticipate what's probably going to happen. So here's a short section of the clip. So two CEOs sign a contract and they stand to face each other. So what's probably going to happen here? Well, they're probably going to congratulate each other in one way or another. But there's actually a small twist that you'll see when I show you the full clip. So let's see the full clip. They stand up and up and up. So this is an example for a joint interaction, even though in this case it actually was an unsuccessful one. So a joint action in cognitive science defines any form of social interaction whereby two or more individuals coordinate their actions in space and time. So space and time really play a very critical role in this case of in these kind of joint actions. And ultimately what we're trying to do in human-robot interaction, many times at least, especially for the case of physical human-robot interaction, is to mimic this type of joint action. But in our case, we have a robot interacting with a human partner. Now, if you dig deeper into the cognitive science literature, you'll see that prediction, especially real-time prediction of action, is often highlighted as a key ingredient in order to realize successful joint action. So in order for two people to interact with each other, two or more people to interact and synchronize their actions with each other, they need to constantly make predictions and anticipate each other's actions, intents, and so on. And three questions, sub-questions that are often mentioned in the cognitive science literature related to anticipation is what, when, and where. So in some cases, the what goes awry. So one case here, so in this case, one person predicted that it's going to be a bow, the other one predicted that it's going to be a handshake. So they have different actions that they anticipated. Sometimes we anticipate the timing wrong. So in this case, when the when goes wrong, we can end up with something like an awkward handshake. And I think many of us have experienced this where the timing between us and the interaction partner is slightly off. And so it's not only about doing and anticipating the right thing, it's also about anticipating when this joint action is going to occur. And finally, obviously, it's also important to align the actions in space also. So in this case here, there was supposed to be a handshake, and then it didn't work out because they never really met. So ultimately, we can conclude from this that prediction really drives coordination in time and space and is a critical ingredient for joint action. And so that leads me to one of the main arguments of my talk, is that we need to think about prediction in order to create responsive robots, robots that engage with human interaction partners. And we will see that it's not only about responsiveness, it's also about proactiveness. So we can incorporate proactiveness into this model. However, the main argument that I'll be making is that we need to go away from the slightly traditional view of separating prediction and response into two sub-boxes or two separate boxes. Rather, I'd like to look at it as one combined box that combines prediction and control, where prediction and control are two sides of the same coin. But if we want to get there, we also need shared representations that allow us to efficiently do both prediction and control. And so the other point that I'll be making throughout the talk is that in order to get there, we really need models that allow us to reason both about space as well as time. We need to do this jointly. We need to jointly reason about space and time. We have many really, really good models for space. However, when it comes to reasoning about time, there are way fewer models. And I think there's something that we as a community probably need to work on. And some of this was already alluded to in the previous talks. And so finally, what I'd like to introduce in this talk is a method that I call Bayesian Interaction Primitives. And that's something that we at Arizona State University have been working on. So in my lab, the Interactive Robotics Lab. And it's basically a representative of such a shared representation that combines prediction and control. And so that's what I'll like to dive into a little bit more in detail next. So next I'd like to talk about how we can learn human-robot interaction using these interaction primitives. So interaction primitives are ultimately nothing but a data-driven framework to learn human-robot interaction from demonstrations. And the main idea is to extract joint probability distributions that model the mutual dependencies between interaction partners, both in time as well as in space. So think about, for example, a high five. So for a high five, these two interaction partners need to make sure that they're in synchrony in time as well as in space. So if one moves to the left, the other one should follow. The key ingredient in interaction primitives is to extract these joint probability distributions, in other words, a generative model that actually captures this relationship, the joint distribution between person one and person two. Once we have done that, we've extracted the interaction primitive, we can then use it in order to perform probabilistic inference for both prediction and control. So think about a situation like this, where we observe the actions of person one, and then we can condition on them in order to generate a probability distribution, a conditional probability distribution that tells us what person two most likely would have done in such a scenario. So it tells us what most likely would have happened in such a scenario given our demonstrations. And just as a reference, typically in our approach, we use between 50 to 100 demonstrations, so kind of more on the low sample side. But not only this, using this framework, we can then also ask different types of questions. For example, we can condition on the past in order to predict the future. So we can condition on past actions of person one to identify what the future actions of person one are going to be. And so hopefully this highlights the tight coupling between prediction and control. So let's make this a little bit more concrete by taking a concrete example. And you'll see in this example that I focus much more on kind of lower level movements, physical coordination between agents involving many degrees of freedom. So in this case over here, we're learning how to throw and catch from example. So in our demonstration phase, we record demonstrations, as I said, about 50 demonstrations, by having two people kind of one throw the ball and the other one catch it. In order to record the data for the robot, we are actually kinesthetically moving the robot in this case. And so once we've done that, we embed our data into a specific basis function space that facilitates learning and adaptation. And I'll talk about that in a second, a little bit more in detail. Note also that we can use our approach with multiple modalities. And multimodal learning is something that has been mentioned a couple of times today. By using multiple modalities, we can make sure that we leverage different information from different sensor modalities. So each one of them may have different advantages. And so now we come to the actual Bayesian interaction primitive. Bayesian interaction primitives model our distribution, the joint distribution, as an ensemble. And in this ensemble, each one of our demonstrations is one element or particle in this ensemble. And so we don't really have to fit any parametric distribution. We're using here a non-parametric distribution. As a result of that, we can capture all of the multimodality and kind of the awkward structure potentially in our data set. So this is a training phase. In the reproduction phase, we can then observe what one of the interaction partners is doing. And now the robot is on its own. So it would have to figure out what to do in this scenario. So we can condition on the live data from a person. And based on that, we can then perform our prediction and response generation. So what you see here is the red part, that's the observed part of the interaction. And then based on the observed part, we get a probability distribution over future evolutions of the observed behavior. So the blue line over here is actually the mean of the distribution, but since we are in a non-deterministic environment, there may be multiple different evolutions of this behavior. And so that's highlighted here in these samples, so these red trajectories and predictions that we see there. And then based on that, we can actually then drive the robot and control the robot to go to those locations. That happens automatically because we actually can infer, make predictions and inferences about the robot joints. So we immediately get the right values for the robot in order to perform control. So now let's take a look at this transformation, the embedding that I talked about in the beginning. So when we record our data, we transform it into a specific embedding that enables efficient learning of the giant probability distribution while also taking into account the temporal and spatial aspects. So in particular, what we do is we represent time using a phase variable phi. So rather than having a global clock, some sort of global timer, we have a local clock, that's our phase variable phi. At the beginning of the interaction, it's at 0, and at the end of the interaction, it's at 1. Also, we take our spatial data, all of the sensor data that we have, and we project it onto a discrete set of basis functions. In other words, our trajectory, so that's here this dotted line, that's represented as a superposition of basis functions. And the weight vector W is a compact vector that represents all of the spatial aspects of our interaction. Now, so far, this is not necessarily a new idea. This is something that has been repeatedly used in the imitation literature, imitation learning literature, and is based on concepts from Eisbert and Nakanishi. However, what we do is multiple things. One thing is to augment this vector by having both a representation for both of the agents. So we're not only modeling a single agent, we're modeling both of the interaction partners. But we're also creating predictive distributions over these weight vectors that allow us to perform inference and infer probabilistically all sorts of, make predictions about the future and all sorts of other variables. Okay, now let's take a closer look at this spatio-temporal inference. In particular, we model our state as a triplet that combines the temporal location. So we want to figure out where are we in time in order to synchronize our actions with our interaction partner. We also have a temporal velocity that tells us how fast we're accelerating and decelerating in time. And finally, the W vector is the previous vector that contains the basis weights, which is nothing but a representation of the trajectory shape. The inference step then allows us to perform inference over both of the spatial and temporal parts. So when we perform inference, we get a probability distribution over phi that tells us where we are in time. So for example, here in this case, it tells us, well, we're probably around 20% into the interaction, but there is some variance around that. So we can also capture how uncertain the robot is about where we are in the interaction. Similarly, by performing spatio-temporal inference, we can also get these different predictions about how the spatial trajectories are going to continue into the future. So again, the red part here is what's observed. And for that, we use the phi variable that we've estimated, so the probabilities of the phase variable. And then we can use the rest in order to estimate how the remaining 80% of the trajectory are going to continue. So this is what we're doing, but not how we're doing it. The how is done using approximate inference over our ensembles. So again, in our case, we represent our probability distribution, the giant probability distribution, as an ensemble where each one of our ensembles or ensemble members is one of the demonstrations that we recorded. One thing that's nice about this is that we don't have to have a parametric version of this. We don't need to fit a Gaussian or any sort of distribution into this. But it also means that we can use both for our prior as well as for our posterior this ensemble. Now this may look similar to particle filtering. However, we use a specific inference process that allows us to get away with way fewer particles or ensemble members than you would normally have in a particle filter. So in our case, as I said, we typically use somewhere around 50 to 100 samples. So we have only 50 to 100 particles, which typically for a particle filter would not be enough to perform inference in really high dimensional spaces. So as I mentioned, we don't need to start with parametric assumptions. We can just initialize our distribution from our demonstrations. Also, our inference process does not need any Taylor linearization. We can use for the forward prediction as well as for the measurement function, we can use a nonlinear function G and H over here. And that allows us to calculate the posterior again as an ensemble. And actually this process is really efficient. We've been running this on all sorts of robots and embedded systems. So now let's get back to throwing and catching. As I mentioned before, we use different data modalities to record the movements. And so even if one data modality has high noise or completely breaks down, we can still continue with our inference. The distance between the robot and the human in this case is about 3.7 meters. And kind of here we see also some samples from our training set. So now let's get to the actual business. So person throws the ball, the robot catches it. And in the next videos, you'll see that the student is also blindfolded in some of them. And again, the robot is able to generate the right actions by just observing the actions of the human. Now, in this case, you may say, well, this is a very specific type of physical human-robot interaction where there's some distance between the human and the robot. And of course, prediction makes sense when you do throwing catching. But can prediction help in more close contact interactions where you only have a second or a fraction of a second until the interaction starts and until it finishes? Well, that's something that my student, Joe, investigated in an internship at Honda Research Institute. And so this is a collaboration between HRI and ASU. And so in this task, Joe tried to learn how to hug. So we have over here this cute robot on the right side. And we're trying to teach this robot how to hug a person. So what you see here is the training process. There's a person standing in front of the robot. And now the robot also has tactile sensors, by the way, in this case. However, typically only late in the interaction does the person really touch the robot. Now, the training process is done using teleoperation. So there's a person here on the left side who's performing the actual interaction during training time. And then we use that data in order to then make our inference, or train our interaction primitives and perform our inference at real time. So next we're going to see the result of that. So this is now a real-time interaction. The person goes in to hug the robot hugs person, and then the robot releases. What you see here in the left upper corner is the estimate of the robot, where we are in time. So this is the estimate, the probabilistic estimate of where we are in phase. And now you can see that the person is going to remain a little bit within a specific part of the phase. And only then will the person release the robot. And as you can see, the robot accurately estimates this progression in time and also the stopping of any progression. Prediction can also make a big difference in this case. Here on the left side, we have prediction. On the right side, we don't have prediction. And you will see that the robot on the right side is much more responsive and you could say even proactive. So here we have a 5% look ahead into the future. So another question that you may ask is, can we actually use predictions to improve safety in HRI? And for that, we performed another study where we actually used the same approach to learn predictive controllers for prosthesis. So one unfortunate thing with many people who wear prosthesis is that they basically change their gait because they develop these stresses, these internal stresses from using the prosthesis again and again. So typically what they do is they change their gait. And so now they're putting a lot of stress, potentially even on the healthy leg. And that's really dangerous. And so what we did here is to incorporate the prediction of biomechanical information in order to create safer control. So what you see here is the lower leg prosthesis that also has a smart shoe that allows us to measure pressure. And what we're interested in is to use this pressure in order to estimate how ergonomic and how safe the current movement of the robot is. But not only that, we can also predict into the future how this internal pressure or the pressure at the feet is going to continue and evolve. And so one thing we can do as a result of that is really predict into the future how, for example, the heel pressure is going to evolve. So that's what you see here in this graph, in this animated graph. The blue line is a 50 millisecond into the future prediction of the heel pressure. And so as a result of that, our prosthesis knows ahead of time how much pressure there's going to be on the heel. In turn, this can be used then for model predictive control, where the action of the robot is chosen in such a way as to minimize this pressure or the pressure on any other joint. Now, in this case, since it's a periodic movement, we also use the twist here. We use periodic basis functions, so in particular for Mises basis functions that can model this periodic behavior really nicely. So now to the end result of this, you can see here a person actually using the prosthesis. This is a healthy person in this case. And so we can compare we can make a comparison between the healthy gait and the gait using this prosthesis. In this case, the person is wearing a bypass. So that way we can, even for a healthy person, we can analyze how the movement of this prosthesis would look like. And as you can see, it looks at least kind of looks very fluent and kind of symbiotic. But at the same time, it would be more interesting to analyze the results, and we can actually verify that the predictions are really accurate. So you can see here in the red part, again, this is the observed part. We can observe some motion, we can predict it into the future. We can also do predictive biomechanics, as I mentioned. We can predict biomechanical variables, even hidden ones, even latent biomechanical variables, for example, internal stresses. This is something that my student is going to describe in detail at ICRA within the conference. So we have a paper there. But we can also use this in order to introduce resiliency to sensor dropout. So here you see the predictions when we use all of the available sensors. So here the red line is really spot on the ground truth. The ground truth is not visible. Here in this case, the blue line is also fairly close to the ground truth. Now, we can also, so if we drop some of the values from our sensor, so in this case, the shoe information, you can see that the prediction degrades and the variance grows, but it's actually still a graceful degradation. Even if we only have a single piece of information, that's the IMU from the tibia, we can still predict the visible, or at least kind of the non-hidden information really accurately. And in this case here, this knee force is actually a hidden variable. Even for the hidden variable, we can create really accurate predictions, or fairly accurate predictions, but the variance is going to grow. And we can, as I mentioned, we can use this for control. And so what that means is we see here the nominal trajectory of a healthy walking gait of this person that we saw in the previous video. And then the blue lines are the trajectories of the ankle angle when using the prosthesis. You can see it's relatively close. And if you compare that with the commercial controller that's provided by the manufacturer for this prosthesis, you can see that the commercial controller would substantially deviate from the nominal trajectory. And so with that, I come to the end of my talk. Hopefully I was able to make a case that prediction really drives the coordination in time and space when we perform joint actions. And this can be very, very powerful for human-robot interaction if we really combine the two by creating shared representations that bridge the divide between prediction and action generation. What you see at the bottom is a bunch of other examples. So the one in the middle, I think I've presented, but the one on the left and the right are other interaction scenarios that we created and developed at my lab, all using the same approach, using the same software. And so applications are kind of varied. So we can use this for prosthesis, social robotics, service robotics. And if you're interested to try this out, we've released our NPRIM library as an open source library on GitHub. And so you can just take the library, throw your data at it, and immediately try it out. And so with that, I thank you very much. And this is the end of my talk. Thank you.
Great. Thanks, Heni, for the nice talk. So are there any questions? I have a question, actually. How would this approach, scale with interactions of many agents? Let's say you would apply this kind of approach in autonomous driving settings, where we have lots of pedestrians, many cars. Yeah, how would you apply this algorithm into these settings?
So the algorithm itself is actually agnostic to the number of agents. So basically you can just add new dimensions, and what it really wants is to learn the mutual relationship between these different dimensions that you have in your feature vector. So it doesn't necessarily have a concept about individual agents. So we have only tried out up to 3 agents so far, because we're mostly focusing on really physical interaction between agents that have multiple degrees of freedom. So rather than focusing mostly on position, which kind of a lot of work is focusing on, things like predicting position and velocity and so on, we're really trying to predict all of the joint angles of the interaction partner, and also predict all of the joint angles that the robot should do as a response. So we've mostly focused on 2 to 3 agents. I think this is kind of the sweet spot at the moment, but ultimately the approach itself is really versatile and scalable, at least. So in principle, it can do that, but I think we need to perform more studies on what happens to the number of data points that you would need for that. So right now you can actually get away with a relatively small sample size. As I mentioned, 50 to 100 demonstrations, and even below that, you can even train agents below that. But 50 to 100 is kind of a good number to ensure safety and so on. But I think it would be interesting to investigate how that changes the sample size if we have more agents.
Yeah. Okay, thanks. So if there are no other questions, I would thank you